Assalamualaikum and hi guys. So today in our statistic class, we are going to discuss chapter 8c, that is the chi-square analysis for categorical data. So in chi-square analysis, we are going to use this chi-square analysis for categorical data. Okay, so if in our previous lessons, for example, in our t-test, z-test, and ANOVA with one-way ANOVA or two-way ANOVA, it refers to the normal data, normal distribution data, but in chi-square analysis, it refers to non-normal distribution data. And usually in chi-square analysis, we calculate the measurement for categorical data, and categorical data is usually referred to the nominal and ordinal. Okay, and all right, I want you to study a little bit about the difference between categorical data and numerical data. Okay, so in numerical data is usually referred to the discrete, continuous, interval, and ratio. Okay, so for categorical data, it usually referred to nominal and ordinal. Okay, so in this chapter, we are going to discuss on the analysis of categorical data by using chi-square analysis. Okay, so what is chi-square or chi-square analysis? So it is referred to the test of independence of variables that is used to determine whether two variables are independent when a single sample is selected. Okay, so for example, the experimental will measures the two qualitative variables to generate the bivariate data. So what is the two qualitative variables? You can refer back into our first chapter in introduction to the statistic that has been described about what is qualitative variables. Okay, so usually in chi-square analysis, we want to measure the relationship between two variables, between two categorical variables. Okay, for example, let's say between gender and color blindness. Between gender and color blindness. So this is two example of the categorical variable. So maybe also between the variable of age and variable opinion, but they all of this is based on the categorical data. That means the nominal or ordinal data. And maybe, for example, between professorial rank and the type of university. Okay, so usually in chi-square analysis, we are going to test the variable, okay, the two categorical variables, and we want to measure either the variables are independent or either the variables are dependent to each other. Okay, so what is the difference actually between ANOVA and chi-square? Okay, in ANOVA, we usually use the ANOVA test when we want to measure the two or more groups of means or average. Okay, so we want to compare the two or more group of means. But for chi-square, okay, chi-square, we are going to use chi-square when we have two categorical variables, okay, and we want to determine if one variable is related to another, okay. And in ANOVA, okay, one variable must be categorical and the other variable must be continuous. But for chi-square, both variables are categorical variable or categorical data. Okay, and usually also in ANOVA, we use the ANOVA test when we want to make the comparison for population mean. But for chi-square, we are going to use chi-square when we want to conduct the test for population proportions. Okay, so that is the difference between ANOVA and chi-square. Okay, but in basic understanding, okay, we can understand that we are going to use the chi-square analysis if our data, if our variables contains the categorical data. That means both IV independent and also DV, that is the dependent variables, are from categorical data. Okay, so when you have both variables, both categorical data, okay, so you might you can continue to use the chi-square analysis. Okay, so what else are the characteristic of chi-square? Okay, usually the chi-square because the chi-square is not the non-normal distribution data. Okay, so the chi-square distribution will extend to the right from 0. Okay, will extend to the right from 0. That means it is skewed to the right. Okay, so usually the data will skew to the right. Okay, however, if the degree of freedom increases, okay, chi-square curve will become will approaching to the bell shape and will approach to the normal distribution. Okay, so although the chi-square is a non-normal distribution data and it's skewed to the right, but if the degree of freedom is increases, okay, if we try to maybe we get the larger sample and it will help to increase the degree of freedoms. Okay, so when the degree of freedom is increased, it will help to approaching to the bell shape and approaching to the normal distribution. Okay, and usually also it means for chi-square is referred to the degree of freedom, and the variant is usually referred to the twice degree of freedom. Okay. All right. Okay. And usually in chi-square analysis or chi-square test, okay, the test can be divided into 3 conditions. Okay, the first one is test of homogeneity. Okay, test of homogeneity. And the second test is referred to test of independence. And the third test is referred to test of goodness of fit. Okay, but however, in this chapter, okay, we are going to refer to the chi-square test of independence. Okay, we are going to learn and discuss about the test of independence for chi-square test. So what is test of independence? So test of independence is usually referred to the test whether the characteristic of the elements of the same population are related or independent. Okay, so usually in the test of independence for chi-square test, we are going to test whether the characteristic of the elements in our population, in the same population, are independent, or maybe they are related to each other. Okay, so basically in test of independence for chi-square test, we are going to refer to the contingency table. Okay, contingency table. So contingency table, the contingency table is refer also to the R, that is rows, and C as column. Okay, so we are going in chi-square test analysis for test of independence. We are going to refer to the contingency table that will have the column and row. Okay, so we study the relationship between the two variables. Okay, as I said, we are going to test the relationship between two categorical data or two categorical variable. So, is one method of classification contingent or depend on the other? So that means that is why we want to use this chi-square, because we want to measure either the two variables are dependent to each other, or the two variables are independent. That means they are not related to each other. Okay. So does the distribution of measurements in the various categories for variable 1 depend on which category of variable 2 is being observed? So if not, the variables are independent. Okay, so usually if we want to state it that if our test shows that the two variables are independent, so it means it refers to the situations, for example, there is no significant relationship between the two variables. But if our test shows that the two variables are dependent to each other, so it means that, for example, we can say that there is a significant relationship between the two variables, or there is a significant relationship between variable A and variable B. Okay, so that is about the test of independence for chi-square test. Okay, so in chi-square test, for test of independence, we are going to refer to the contingency table and refer also to the total cell of the row and columns. Okay. So in chi-square test of independence, we are also going to identify the null and alternative hypothesis. So for chi-square test of independence, the null hypothesis is going to refer to the classifications are independent, and the alternative hypothesis is referred to the classifications that are dependent. Okay, for example, like I said before, for null hypothesis, that is classifications are independent. Okay, so that means it's referred to all the observed variable. Okay, all the test variable or the measurement tests are equal, or they are not related to each other. But for alternative hypothesis, we are going to assume that the variable are related to each other, or the variable are have a significant relationship between each other. Okay, so that is the null hypothesis. Okay, in chi-square test of independence, we are also refer to the observed cell count. Okay, that is referred to O. And I is referred to the row, and J is referred to the column. Okay, and we are going also to estimate the expected cell count. That is referred to E. EIJ, that means I is row, J is column, and also equal to the value of NPIJ. Okay, so observed cell counts or observed frequency is referred to O, and it is usually the real data or the sample data. And the expected cell count or expected frequency, that is E, is referred to the expected data. Okay, what we are expected to. Okay, so that is expected cell count. Okay, let's say if the null hypothesis is true and the classifications are independent. Okay, so if the null hypothesis is true, then we can say that the classifications are independent. Okay, so if null hypothesis is true and the classifications are independent, so the proportions is equal to each other. Okay, is equal. Okay, so this is the formula to make the analysis by using chi-square test of independence. Okay, where the value of Pi and Pj is referred also to the value of row, the total row divided by n, and the total column divided by n. Okay, so this one is referred to row, total row, okay, this one is referred to total row, and this one C is referred to total column. Okay, and you must also get the value of expected frequency or expected count. So this is expected count. So how to get expected count? It is referred to the value of row, total row divided by n times with column, total of column divided by the value of sample n, the total sample. So it is also equal to row, total, this is total row times by total column divided by the total value of the sample. Okay, and then after you get the value of the expected count, okay, then you can proceed to the test statistic. So in chi-square, the test statistic is referred to x square. Okay, refer to x square. So how to get the test statistic for chi-square test of independence? It is x square equal to the total or the sum of total of observed count minus expected count and square. Then divide by the expected count, the total expected count. Okay, and then in test statistic also, you must also get the value of degree of freedom. Okay, because you might going to get the critical value in the chi-square table by refer to the value of degree of freedom. Okay, so the test statistic has an approximate chi-square distribution with df, or degree of freedom, is equal to the value of row minus 1 and times with the value of column minus 1. So you will get the value of degree of freedom. Okay, so now let's see the examples. Okay, in this example, it states that furniture defects are classified according to the type of defect and shift on which was made. Okay, so now they will give you the value of the type of defect and the value of shift. Okay, so now because in chi-square analysis of independence, we are going to refer to the contingency table that is referred to the value or the total cell count for row and column. Okay, so now this total, okay, is referred to the column. Okay, so this one is referred to column, and this total cell count is referred to row total cell count. Okay, sometimes in questions, they only give you the value of the two categorical variables. That means, for example, maybe they only give you the value of 1, 2, 3, okay, and the type is A, B, C, D, but they not give you the value of total. So you must count yourself to get the total. For example, 15 plus 20, for example, let's say 15 plus 21 plus 45 and then plus 13, then you will get 94. Okay, you will get 94. And how to get the total for column? So 15 plus 26 plus 33, then you will get the total of column is 74. Okay, so this is the total value or total sample that is from the total value of column and the total value of row. Okay, so that is 309. That is referred to the value of N, or the total sample. Okay, this one, 309. Okay, and now the question said, do the data present sufficient evidence to indicate that the type of furniture defects varies with the shift during which the piece of furniture is produced? So test at the 1% level of significance. So they want you to test at alpha level of chi-square, that is referred to 0.01. Okay. So first of all, we are going to state the hypothesis. Okay, the first step, we are going to state the hypothesis. So what we are going to say for the null hypothesis based on this question. So the null hypothesis that we can state it is type of defect is independent of shift. Okay, and for alternative hypothesis, we can state that the type of defects dependent on the shift. Okay. Okay, now after we stated the null and alternative hypothesis, now the second step, we are going to calculate the value or the total expected count. This is the total of expected count. So the total expected count, if you refer back to the formula, it is refer to the total row. This is row, total row times by total column. Okay, by total column. Okay, this is the example from row 74, total row that is 74, and the total column that is 96. Okay, let's see from the table. Where is the position for the total row that have 74 and total column that have 96? Okay. Okay, for 74 is here and 96 is here. Okay, so to get the value of the total expected counts, we must time the value of 96 with 74 and divide by the total value of sample, that is 309. Okay, so that's how you will get the total expected count, that is 22.99. So the 22.99 is referred to this observed cell count. So it is 22.99. So this one is 22.99. The expected cell count, 0.99. Okay, if the table, or they don't give you the table, just the value, okay, the value each of the shift and the value each of the types, that is a type A, B, C, or shift 1, 2, 3, and they don't give you the table. So I have strong suggestions to you to draw your own table, because by using the table, you can more clear and understand, okay, what step that you need to do based on the table that you have drawn. Okay, so now they give you the table, okay, but the table is too small for you to insert the value of the expected count. This one. So if let's say the table is small, okay, I suggest to you to draw the other new table. Okay, let's say the other new table for your own reference and for your own understandings. Okay, because this will help you more easier to make the analysis. Okay, and then you create, for example, let's say this is your table expected. Let's say this is the table of expected counts. Okay, so this is table of expected count. Okay, so this is the type, and this one is refer to types, and this one is refer to the shift. Okay, so let's say this is 1, 2, 3, and then A, B, C, and D. Okay, after you count your each of the expected value, okay. Let's say in this example, it counts for A. It counts for A 2. Okay, so how to get the expected count for A2? So you must times 96 with 74. That is the total value of the row times with total value of column, and divide by the total value of sample. So 96 times 74 divide by 309, then you will get the expected count is 22.99. So now you can insert the value of expected count into your expected count table, that is 22.99. So how to get the A1? So you're going to use the same formula, and you must count for all the each of the value that have been given. Okay, so now for 1A, you must this is referred to the 15. So 15 is referred to the total column is the 74, and the total row is 94. So you must times 94 with 74 divide by 309. Okay. Again, how do you want to get the value, the total expected count for A1? So you must times the value of total row, that is 94, times with 74, the total value of count, and divide by the total value of sample, that is 309. So you will get 22.55. So this one you will get 22.55. So you can insert into your expected count table, that is 22.51. Okay, so you must get all the value for expected count before you proceed to the test statistic of chi-square. So you must times all the total row and column and divide by the total value of the sample, and then you put all the expected count value in your expected count table. So you must insert all the value here. Okay, insert here. You must count for 2B, 2C, 2D, 3A, 3B, 3C, and 3D. Okay, so after you get all the value of expected count, okay, then you can proceed to the next steps. That means you can proceed to the test statistic. So test statistic for chi-square is referred to x square. Okay, it refers to x square. So x square is the total value or the sum of the total of the sum of the sum or the total of the value of observed. Okay, the total observed minus the total of expected count, and then square and divide by the total expected of count. Okay. Let's say from the table, what is the first value for observed count or observed frequencies? Okay, it is referred to 15. Okay, 15. So now, okay, you insert the value in this formula, that is 15, and divide by the total value of expected count. What is the total value of expected count for observed count that is 15? So if you refer back, okay, in this table, so 15, the total expected count after you count it, previously you have count it, okay, and it refer to 22.55, or you can refer back to all the expected count table that you have draw, and you have insert the value of expected count. So 15 is referred to 22.51. Okay, so now you insert the value of expected count, that is 22.51. Divide by the total value of expected count, that is also 22.51. Okay, then you must plus with the next observed cell count, that is referred to this one, 26. So 26, what is the expected count? It's referred to 22.99. This one. Okay. So 26 minus the expected count is 22.99. And then square divide by the same value, that is the expected count for 26, that is 22.99. So you must add all this value until the last observed cell count, that is 20. Okay, this one you must add until 20, the last value. Okay. So when you insert all the value into the test statistic X or X square formula, and then you calculate all the value, you will get the answer is 19.18. So your test statistic X square or chi-square is 19.18. Okay, so now in third step, you must find the value of degree of freedom. Okay, if you refer back to the previous slides, it shows that the simple formula to get the value of degree of freedom is equal to the row, the number of row minus 1, and times with the number of column times 1. So now, based on this equation and in this table, okay, we have 3 row and 4 column. Okay, 3 row and 4 column. Okay, if you go back to the table, you can see that we have 3 row and 4 column. So now, R is referred to 3 and C is column referred to 4. So now 3 minus 1 times 4 minus 1 is equal to 6. So the degree of freedom is 6. Okay, now you can start to refer to the chi-square table after you get the value of degree of freedom. Okay, based on the question also, okay, based on this example, they want you to get the test significant level at alpha 1%. That is referred to 0.01. So you can refer to the chi-square table. Okay, refer to chi-square table. Okay, when you refer to the chi-square table, you must refer to the alpha value that is 0.01. Okay, because they want you to test the significant level at 0.01. Okay, and then you must also find 0.01 that has the degree of freedom is 6. Okay, so if you refer to the chi-square table with significant alpha 0.01 and the degree of freedom is 6, then you will get the answer is 16.812. This one. Okay, this one 60.812. Okay, now we can do the comparison. That means if you also try to draw the graph, okay, but it is skewed to the right. Okay, so let's say we get the value is 16 point, this one 16.812. Okay, so 16.812 is around here, 16.812. Okay, and now we get the test statistic. Our test statistic is 19.18. Isn't it? 19.18. So it is around here, 19. Okay, 19.18. So now we can see that it is fall in the rejection region. So fall in rejection region. So in our fourth step, we are going to conclude our hypothesis. So in chi-square also, okay, we are going to reject the null hypothesis if the value of test statistic is greater than the value that the value or the critical value that has been referred to. Okay, so now, okay, we are going to say that we can reject the null hypothesis, or the null hypothesis is rejected because there is sufficient evidence to indicate that the proportion of defect types vary from chief to chief. Okay. But another point also, another important point also, okay, in chi-square analysis, you don't have to divide the alpha value by 2. Okay, because it is non-normal distribution data, so it's skewed to the right. So you don't have to divide the alpha value into 2. Okay. So that is the steps of the analysis for independence test for chi-square analysis. Okay. Okay. This is also the example on how you are going to interpret the expected cell count. Okay, the expected cell count. Okay, they say that for example, expected counts are printed below observed count. So this one, this is the expected count. Like we have count earlier, like I show you in the table. Okay, and chi-square distributions are printed below expected count. So this one, chi-square contributions are printed below expected count. Okay, so this is also another example of table that you can draw for your own understanding and your own reference. Okay. Okay, let's say if you are going to, you want also to refer to the p-value. Okay, you can also refer to the p-value. For example, let's say the test statistic that you get is 19.18 or 19.178. Okay, or if you round it to 2 decimal places, that is 19.18. Okay, so the test statistic you get is 19.18 and the degree of freedom you get is 6. So you can also refer to the chi-square table and you can try to find what are the p-value that are approaching to the value that is 19.178 and with the degree of freedom is 6. Okay, for example, if you refer to the chi-square table, if the chi-square is 18 something, okay, 18 something, and then the degree of freedom is 6. Okay, so the p-value is going to refer to 0.005. Okay, so if let's say the chi-square is 19, that's mean greater than 18, and the degree of freedom is 6 also, you can see in the chi-square table that the p-value should be less than this value, should be less than 0.05. So that means it approaching to 0.04. Okay, so 0.04 is also less than the cut-off point for significant level, that is 0.01 and 0.05. Okay, as we discussed earlier, the cut-off point for significant level is usually referred to 0.05 and 0.01. So now the p-value, if we refer to the chi-square table, we will get the p-value is 0.004. That means it's less than 0.01 and 0.05. So we can reject the null hypothesis. So we can state that there is sufficient evidence to indicate that the proportion of defect types vary from shift to shift. Okay, so what we are going to say for the chi-square analysis. So when you calculate the expected cell count, okay, when you calculate the expected cell count, okay, the expected cell count, like I show you before. So when you calculate the expected cell count, then you find that one or more value is less than 5. Okay, that means when you try to calculate your expected cell count and then you get maybe 1 or maybe 2 or maybe 5 or 3 or more of the expected cell count value, that is the value is less than 5, okay, then you can go to another options. Okay, the first option is try to choose a larger sample size. Okay, the larger the sample size, the closer the chi-square distribution will approximate the distribution of your test statistic. So that means if you get the larger sample size, you will get the value of expected cell count is also larger, and this will help you to get the smooth chi-square analysis. Okay, and then another options also, you can maybe you can combine one or more of the cell. Okay, so maybe you can combine the cell with a small expected cell count. So that means when you combine the cell, so it will be not many cell count. Okay, but it will give you the small expected cell count. Okay, but it is okay to use if you want to choose to get a larger sample size. Okay, and also if you want to combine one or more cell into a small expected cell count. Okay, so that your expected cell count value, when you count it, it is not less than 5. Okay, so if you count your expected cell counts and then you find that one or more your expected cell count value is less than 5, then you must choose these two options. Either you choose to have a large sample size, or the next option is you can combine the expected cell count to be small expected cell count. Okay. All right, so that's it for chi-square analysis for test of independence. If you have any question, you can ask me. And please also refer to these lecture notes that I will attach in Putrablast. And I will also attach another 2 examples of the chi-square calculation for test of independence through short videos in Putrablast as well. Okay, so please feel free to refer to the lecture notes and refer to the short notes for extra tutorial how to calculate the test of independence for chi-square analysis. Okay, so that's all, and I wish you all the best. Thank you.